Suppose this semicircular disk has a mass m and its radius is r. Okay, our aim now is to derive derive the position of its center of mass. In the last class itself, we had discussed that this has a line of symmetry, the y-axis, as you can see, and the center of mass lies somewhere on the y-axis. We know that. If any system has a line of symmetry, center of mass lies on that line. So what we are looking for, or what we are trying to derive, is the y-coordinate of its center of mass. The formula for y-coordinate of center of mass of a continuous mass distribution is integral y dm divided by integral dm. If you want to integrate this, you need to express dm in terms of dy. Okay, but let's understand what dm is, dy is. Generally, the formula for position of center of mass is sigma mi ri divided by sigma mi, where mi is the mass of the ith particle and ri is the position of the ith particle. So what mass is at what position is what you need to know. Similarly, if you want to integrate y dm, dm is the mass whose position is y, or whose y coordinate is y. Okay, so what we did is we took a random y coordinate, some y value we assigned. At that height, at that y coordinate, what all mass is present, we have shaded it already. So that rectangular mass that you see, actually it's not a rectangle, the edges are curved. Okay, but whatever shaded region is there, that region's mass is dm. Total mass, the total not shaded, I should say, colored region that is there has a mass m, but this thin region that we have shaded has a mass dm. That is the mass present at that height. Now, if you want to integrate y dm, you need to express dm in terms of dy. Now, in the diagram, if you observe, dy is nothing but the width of the shaded region, width or height of the shaded region. We need to express the mass dm in terms of that height. How can that be done? Listen, when we had linear mass distributions like a rod or a semicircular ring, when we wanted to express the mass of an element, what we did was we took help of lambda. For linear mass distributions, you take help of lambda is equal to dm by dl, and you can express the mass of an element. Now this here, a semicircular disk, is an areal mass distribution. Mass is spread over an area, not a length. So you take help of something called areal mass density. That is what I had given you about in the worksheet, yesterday's worksheet. We use something called areal mass density, denoted by the symbol sigma. Can any of you guess the definition of areal mass density? Linear mass density was mass per unit length. Then what will areal mass density be?
Sir, mass per unit area.
Mass per unit area, correct? So you can say sigma is equal to, if it's the same all over the object, then you can call it as total mass by total area. Just a moment. Okay, if it's a uniform mass distribution, you can call sigma as total mass by total area, mass per unit area. If it's non-uniform, or even if it's uniform, you can also call it like this: small mass by the small area that it occupies. Okay, for linear mass distribution, we had written lambda is equal to total mass by total length if it is uniform, or generally it is dm by dl, small mass by small length. Similarly, we are writing an equation for areal mass density. Whenever mass is spread over an area, you will use this idea. And why I am spending so much time on these ideas is because you will use the same ideas in the next chapter, gravitation, to find out something called gravitational field of a given system. In fact, in this chapter itself, we'll be using these ideas once again to derive something called moment of inertia of a system. You need to know how to split a given system into smaller parts. Okay, even in 12th class electrostatics, you learn about something called electric field, electric potential. There also you'll have to split a system into smaller parts and analyze. Okay, so how to split a system into smaller parts is what you are effectively learning now. Since this is an areal distribution of mass, you have to use the areal mass density sigma, which is dm by dA. Therefore, you can write dm, or you can express dm as sigma dA. So if you want to express the mass of a certain region of this system, you should multiply the mass density, areal mass density, with the area of that region that you are interested in. Okay. Now, to integrate, now our aim is to find out the position of center of mass of this system. But in that integration, we have stumbled upon this. We need to express dm in terms of dy. That is what we are trying to do now. Dy is not an area. Dy is just the height of that area, shaded area. Let's call this total shaded area as dA. This complete shaded area is dA. Why are we using the symbol d? Why don't we just call it a? dA implies a very small part of the area, very small part of the total area. A is the complete area. Okay, so since this is a very thin element whose width is just dy, the area will be very small. That's why we use dA. You have to get used to all this. So we can write dm is equal to sigma into dA, but that is not, that won't help us. We need to express dm in terms of dy, which is the height of that area. How to do that? Can any of you tell me what is the shape of the shaded area? What is the shape of the shaded area?
Semicircular.
Ah,
So the black line.
I'm not asking
Ah,
colored.
so
Colored area is
rectangle.
semicircle.
So rectangle. Right.
Are you sure it's a rectangle? Look at the
So no,
edges
so the edges are rounded, but it's
curved.
almost. Yes, sir.
Almost a rectangle. Good that you use that term also. Listen, all of you. The element that we have considered, the area that we have shaded, looks somewhat like this. There's a curved edge here. There's a curved edge here. Okay. This is what the shaded area looks like. The thickness is dy. Thickness or the width is dy. We don't know the length yet, but this is what it looks like. But see, the width is dy, right? dy literally means a very small change in y. How small? So small you can't even tell how much it is. Okay, so it's actually a very thin element. You won't even be able to notice its width. For us to be able to visualize, we draw it like this. These are all enlarged diagrams, but actually it's not this thick, this wide. Okay, now if the width is very less or the height is very less, what happens? The sides, the curved edges that are there almost appear straight. You won't be able to notice the curvature at all. Okay, this edge almost appears straight. Yusuf, do you agree with this or not?
Yes, sir.
If the width is so small, the curvature will not even be appreciable. It will appear almost like a straight line. So now what is this shape? It's a trapezium. Okay. dA then becomes the area of this trapezium. Fine. But see, it's quite complicated to express the area of a trapezium, and you actually don't have to do it. dA is the area of this trapezium. That's fine. The trapezium can be considered as a rectangle plus two small triangles, one on that side and one on this side. Rishi, do you agree with this or not?
Yes, sir.
The actual dA that we are looking for, the actual shaded area that we are looking for, is the area of the trapezium. But the trapezium's area can be considered as a rectangle plus two small triangles on either side. Now see, the width of this, okay, I can just copy paste it and make it shrink, I think. Yeah. The height of this trapezium is very, very small, tending to 0. If you look at it that way, consider it like this. Fine. Then most of the area of the trapezium is the rectangle itself. The parts that you are missing out, the triangular parts, one on this side and one on that side, I'm shading them in yellow, are not even noticeable. They're not significant compared to the rectangle that you have in between. Okay. So if the trapezium is very narrow, if the height is very small, then we can write area of the trapezium is approximately equal to area of the rectangle itself. You'll be missing out a small triangular part on that side and this side, but the part that you are missing out is actually negligible. Okay. This is a mathematically valid approximation. In fact, I should not have shrunk it like this also. What I should have done is something like this. I should have taken another line very close to the base of the trapezium. I should actually take it like this. If I consider that way, you look at the rectangular area that I get. All this all the way till here. And okay, just a moment. I don't know suddenly why this thing became oversensitive. I'm not even touching the screen. Okay, this becomes a rectangle, and the triangular part that you're missing out is not even noticeable. You look at the small yellow part that I have drawn now, not the one which was drawn before. Okay. So you won't even notice what you're missing out at on either side, the triangular part. Okay, so the area of this trapezium is approximately equal to the rectangle's area itself. And how do you, what is the expression for an area, for the area of a rectangle? Can any of you tell me? What is the expression for area of a rectangle?
The
Formula
length
for
into
area of
width.
rectangle. Yeah, length into width. Okay, thank you. Now let's call this as x. If one side is x, the other side will also be x. Okay, there is a line of symmetry. Y-axis is the line of symmetry. If one side width is x, the other side will also be x. So the total, I should not call width, length. The total length is 2x and the height is dy. Therefore, dA, the area becomes 2x multiplied with dy. Now we are getting somewhere. We are able to express area in terms of dy. And if you can express area in terms of dy, you will be able to express mass in terms of dy. But still there is, I mean, we are not ready to integrate it yet. We got dm in terms of dy, that's fine. But in that process, we have introduced another variable, x. Now, how is x a variable? From element to element, you all tell me, from trapezium to trapezium, will the width vary or not? Okay, I'm again saying width, I'm sorry. I should call it length. Will the length 2x vary from trapezium to trapezium or not? Clearly it varies.
Yes, sir.
Okay. So for all the y coordinates, the x value is not the same. Therefore, we have introduced another variable, which again makes it impossible to integrate. Okay. Our aim was to integrate y dm and divided by the total mass, integral dm. To do this, we are trying to express dm in terms of dy, but we got it like this: dm is equal to sigma into dA, where the area is now expressed as 2x into dy. So we have introduced another variable x. We won't be able to integrate now. You can't integrate x with respect to y. Now what you have to do, you need to get a relation between x and y. Let's see if any of you can tell me the relation between x and y. Look at, observe this diagram carefully. The radius of the semicircle is r. Tell me if you can relate x and y in any manner. Can you write an equation which involves both x and y? Okay, I'll give you a hint. X and y are related by the radius. Think about it. Okay. See, let me repeat. I need a relation between x and y, which means I need an equation which consists both x and y.
Where r square equals to x square plus y square.
Good. Pythagoras theorem. Now, the distance from here to here is the radius. Now you clearly see a right angle triangle forming there. So r square is equal to x square plus y square. Okay. Let's make use of that. So you get x square is equal to y square minus r square, and you get x is equal to under root y square minus r square. So we got x in terms of y now. Then again, we are getting somewhere now. What we wanted to do was integrate y dm and divide it by integral of dm. Integral y into dm became sigma into 2x into dy. Divided by integral dm is still there. Let it be. Now, sigma is a constant, 2 is a constant, let it be. X is written as under root y square minus r square, and you are left with dy. Divide by integral dm. Now the entire integral is in terms of y in the numerator, as you can see. 2, sigma, the radius r, these are all constants. The only variable is y. Okay, so now we have expressed it completely in terms of y, but integrating this is a challenge now. Simple integrals we could have done, integral x power n dx or integral y power n dy we could have done. But this looks complicated. Can any of you tell me how to integrate this? Or do you have any idea how to integrate this? It's quite complicated. You are not expected to know also. Maybe in your 12th class you will learn how to integrate such functions. Or there is a way you can use something called integration by substitution, but leave it. Look at what we have done. Our aim was to find out the position of center of mass of this semicircular disk. We drew the line of symmetry. We are trying to find out where the center of mass lies along the line of symmetry. So for that, we took integral y dm divided by integral dm. To integrate y dm, we had to express dm in terms of dy. So we visualized dy, okay, and the mass that lies at that particular height, and the mass was spread over a trapezium. Trapezium we approximated to rectangle. We express the area of that rectangle. We even express the mass of that rectangle. And we substituted here, but we ended up getting a very complicated integral. So this approach is valid, but won't get us anywhere because it is difficult to integrate this. It's time taking, can be done, but we won't proceed this way. Okay. You may ask, sir, why did we start going this way if we are not going to proceed this way? Just to know what works and what doesn't work. Okay. In fact, for some questions, you will have to proceed like this only. I'll give you examples where you'll have to use this method. Okay. For now, you don't have to use that method. So what's the other way in which we can find out the position of center of mass of this system? Let's see. Just a moment, let me clear all this. Y-axis is needed. Okay. The y-axis is a line of symmetry. So what we are still looking for is the y coordinate of center of mass itself. And there is one formula for y coordinate of center of mass, integral y dm divided by integral dm, but that did not work. Okay. Can one of you tell me what other ideas we learnt about center of mass? Ideas. Like one idea we discussed was that the center of mass of a two particle system divides the line joining them in the ratio m2 is to m1. That is one idea. We know the ratio in which center of mass divides the line joining two particles. Like that, what other ideas about center of mass did we discuss? Symmetry is one idea. We have already used it, and we concluded that the center of mass has to lie on the y-axis. There is one more idea we discussed about center of mass. Can any of you recollect and tell? Okay. What was the logic or idea we used to derive the center of mass of an L-shaped object? Some of you were, most of you were there in the last class or the class before that. What was the idea we used to derive the position of center of mass of the L-shaped object?
So we treated them as two different objects.
Correct. We treated it as a combination of two systems. Okay. That is the other idea that I'm referring to. The center of mass of a combination of systems. Okay, these ideas are very important. The center of mass of a combination of systems can be found by treating each system as a single particle placed at the center of mass of that system. Okay, like when we try to derive the position of center of mass of that L-shaped object, we treated the L-shaped object as a collection of two rods. This rod was treated as a single particle placed here, and the other rod lying along the x-axis was treated as a single particle placed here. We gave them mass proportional to the length. One mass was taken as 2m, the other mass was taken as m, and we used the 2-point formula for the center of mass. Okay. We are going to do something similar here because we have used the other ideas, we didn't get anywhere. Okay, this is the only idea we are left with. So what we are now going to do is we will treat this semicircular disk as a collection of smaller systems whose position of center of mass we already know. Okay. Now, one of you recollect and tell me, what are the systems whose center of mass we have already derived so far? What are the different systems whose position of center of mass we have already derived?
A uniform circular ring, then
Uniform semicircular
circular.
ring. Yeah, circle also we had discussed. Semicircle we had discussed, right?
Yes, sir.
So, yeah, we had derived the position of center of mass of a uniform straight rod. We even derived the position of center of mass of a uniform semicircular ring. Now, this is a semicircular disk. It's an aerial distribution. But what we are going to do is we are going to treat it as a collection of semicircular rings of different sizes placed one over another. Okay, I'll explain what I mean by this. So consider something like, just a moment, I'll adjust this. Okay. Now see, the black thing that I have drawn here is a semicircular ring. It's not a disk. It's not a full disk. It's just a ring. Fine. The semicircular disk, which is the blue colored one, okay, is a collection of many rings like this. Okay, you can consider one ring like this, then consider another ring bigger than this one. I'll help you visualize. You can consider another semicircular ring like this, slightly bigger than this one. Okay, and you stack all those rings one over another or touching each other. What you get is the disk that is given to you, semicircular disk that is given in the problem. Do you all agree with this point or not? Saket, are you able to visualize it like that? The disk as a collection of rings.
Yes, sir.
Okay. Pawan, is this idea clear?
Yes, sir.
Yusuf? Are you able to visualize the disk as a collection of semicircular rings like this?
Yes, sir.
Huh. Okay. And why are we treating it as a collection of semicircular rings? See, we could have taken the disk, semicircular disk, as a collection of rectangular strips, but that led us to a very complicated integration. So we didn't proceed along that way. The only other system whose center of mass we know is a semicircular ring. So we treat the semicircular disk as a collection of rings like this. Okay.
ఎందుకు ఇది పనిచేయడం లేదు
పని చేస్తుంది. Keep yourself muted. Okay. Now, see, as I said, you have to treat it as a collection of semicircular rings like this. Each ring, each semicircular ring has its own radius. Okay. And that radius varies from ring to ring. So small r is going to be a variable for us. Okay. And the ring that I have shown here has some thickness as well. Width or thickness, you can call it anything. We can call it as dr, the small change in radius from one ring to the next one. Is this okay to all of you? Any doubt in this? I'm calling the radius of that shaded ring, that black ring, as r, and its thickness or width as dr. That's fine, no? Dr means change in r. So when you move from one ring to the next ring, the distance that you are going to move through is dr. That's fine. Now, the ring element that we have considered here occupies some area of this semicircular disk. You can call this area as dA. It occupies some part of the area. Okay. Every ring element that you take has some area. Fine. What is our aim? Our aim is to derive the position of center of mass of the semicircular disk. For that, we are considering the semicircular disk as a collection of semicircular rings like this. So we are using the idea of center of mass of a combination of systems. Now the black ring that I have shown here, semicircular ring, is one of the systems. Okay. Its area is dA, and assume it has a mass dm. We still don't know how much it is. We have not derived it. But it's a uniform semicircular ring. Can one of you recollect and tell me from the last class, what is the height of center of mass of a uniform semicircular ring? That's the last derivation we had done. What is the height of center of mass of a uniform semicircular ring?
2r by pi, sir.
2r by pi, correct. So the center of mass of this ring that we have considered will be at somewhere here, whose y coordinate is 2 small r by pi, because its radius is small r. Why are we bothered about its center of mass? You see the idea that we have written on the right side. Center of mass of a combination of systems can be found by treating each system as a single particle placed at the center of mass of that system. Now, the system that we have considered is a semicircular ring. We have to put it all at one place. What is the place where you will put all that mass? The center of mass of that semicircular ring, that dot that I have shown there. Okay, so you'll assume all the mass dm is present at this y coordinate 2r by pi. Okay, so the semicircular ring's mass can be treated as a point mass placed at that distance or placed at that position. Is this clear to all of you? Is this step clear? Why I marked the dot there? Why I assumed all the dm to be present there? Pawan, did you understand?
Yes.
Okay, Yusuf, is it clear? We are trying to replace that semicircular ring, the black arc that I have drawn. We are trying to replace it with a single particle. And if you want to do that, you have to put that single particle at the center of mass of that arc. Okay, center of mass of a semicircular arc is at a distance of 2r by pi. So that is where we put the particle. So all that shaded mass that is there, which is in the shape of an arc, lies at that, can be assumed to lie at that point 2r by pi, at that height 2r by pi. Okay. So now, okay, one of you tell me, how many such arcs will make up this complete semicircular disk? If the width of the arc is negligibly small, how many such arcs do we have to take?
Infinite.
Infinite. Good. So each arc is a system and there are infinite such systems. So what you have to do is, if you want to find out the position of center of mass of this combination of arcs, you'll have to do integral of y dm. What is y? Y coordinate of a particular arc. What is dm? Mass of a particular arc divided by integral dm. Integral dm is the total mass. That is easy. Okay. What is the y coordinate of a particular arc? The y coordinate of its center of mass, 2r by pi. You have to integrate that along with the mass of the arc. Divided by integral dm becomes total mass. I'm writing it as it is. Okay. But again, there is trouble here. Small r, which is the radius of this arc, is a variable. It varies from one arc to the next one. If you want to integrate this, you will have to express dm in terms of dr. Mass of the arc has to be expressed in terms of what is dr? Width of the arc. Okay, let me take that semicircular arc aside to be able to visualize properly. This is the semicircular ring that we have considered, arc or ring. Okay, its radius is r. And its width is dr. There is some mass present here, dm. We have to express that mass in terms of that width. Whenever you need to express the mass of an element, the element is the arc here. The original disk is a collection of many such elements, many such arcs. Whenever you need to express the mass of an element, you first need to think of what kind of mass distribution it is. Can one of you tell me what kind of mass distribution is a semicircular disk, the original system? Is it linear, areal, or volumetric?
Aerial.
It's an areal mass distribution, correct. And in an areal mass distribution, mass of an element is expressed as areal mass density sigma multiplied with the area of the element. Now, what is the area of this element? This shaded area. Okay. Writing dm as sigma into dA is not enough. We want dm in terms of dr, thickness. So can one of you tell me how to find out that shaded area? An idea to calculate that shaded areas, shaded regions area. It's an arc which has some thickness. How will you calculate the area? Pawan, any idea? Vanilla, any idea to calculate that area? Or anyone? Okay, suppose I draw something like this. And I ask you to find out, and I ask you how to find out this area. What is the idea?
Area of the big square and the
Area of the
area of
outer square minus area of the inner square. Now what you see here is also similar to that only, no? I mean, it's not a square, okay, but it's an arc which has some thickness. So what you can do is, you can find out this complete area first, okay? And from that, you can remove this smaller area. Pawan, do you agree with this or not? Can we
Yes.
do it? Can be done, okay? What is wrong in that? Fine. So outer area minus inner area is what we are going to do. Visualize the outer area. What is its shape? The region that I am now marking in blue, what is the shape of that region?
Semicircular.
Semicircle. How much is its radius? How much is the radius of the outer semicircle?
R, sir.
R plus dr, sir.
R plus dr. Inner semicircle is R. Okay, this green one, its radius is R. Outer one is slightly bigger. Okay, it is R plus dr. Rishi, is it clear?
Yes, sir.
Ha. So what we now need to find out is the difference between their areas. One of them, the outer one has an area R plus dr. The inner one has an area, okay, radius. The outer one has a radius R plus dr. Inner one's radius is only R. And observe this point very carefully. One of you tell me, what is the formula for area of a semicircle?
Pi r square by 2.
Pi r square by 2. Pi r square is full circle, by 2 will be half circle. Okay. So the outer area will be pi into r plus dr whole square by 2. And the inner area will be pi into r square by 2. And let's simplify this now. Pi by 2 is taken common. R plus dr whole square becomes r square plus dr squared plus 2r dr minus, there's another r square here. So the r square part gets cancelled. Look at what you are left with. The shaded area, which we are trying to express in terms of dr, turns out to be this much. Pi by 2 into 2r dr plus dr whole square. Okay. Now, those of you who learned calculus from me, or those of you who are in touch with calculus, you will be aware that dr is a very small term. How small you can't even tell. Now, when dr is present, dr square will be even smaller, negligible. Why? Suppose you take dr like this, 0.0001, that is 10 power minus 4. Then dr squared becomes 10 power minus 8. That is 0.701. Very small compared to dr, right? So in calculus or in mathematics, it is valid. You can ignore that term. So when dr is present, dr square becomes negligible. Neglect that. What will you be left with? Pi by 2 into 2r dr. 2's cancel. Effectively, you are left with pi r dr. This is interesting. See, what is the formula for perimeter of a semicircle? Length of a
Pi r.
semicircle, pi r. Okay. So what we got here, the final result, is the length of the semicircle multiplied with the thickness or width. Okay. I'll indicate the length in yellow here. This inner semicircle that is there, its length is pi r. Okay, this yellow length is pi r and the width is dr. So effectively what we see or what we get is that the area of the shaded semicircle that is there, not semicircle, I should not call it semicircle, the area of this semicircular ring that is there, okay, thick semicircular ring, its area is nothing but its length multiplied with the thickness. Fine. It turns out to be like this only because the thickness is very small. We are ignoring dr square compared to dr. Remember that. The actual way to find out the area is outer area minus inner area only. But if the gap is very small, like dr, then you can simply take it as length multiplied with thickness. So what have we derived from all this? We got an expression for dA, which is basically pi r dr. Now, why did we want to express dA in terms of dr and all? Because our aim was to derive the position of center of mass, integral y dm divided by integral dm. The dm that we took, the element that we took is in the shape of a semicircle. So first we wrote an expression for y coordinate of that semicircle, which is 2r by pi, its center of mass. We are replacing the entire semicircle with a single point placed at its center of mass. But now the integral becomes 2r by pi dm. You can't integrate r with respect to m. So we are trying to express dm in terms of dr. Dm is what? Mass of this element. How do you find out mass of an element? You first think of the mass distribution. Here it's an areal mass distribution. So mass of an element is calculated as areal mass density sigma multiplied with the area of the element. Okay. How do you write the area of this element? We got it as pi r dr. Therefore, the mass of the element now becomes sigma into pi r dr. Sigma into area, that is nothing but sigma into pi r dr. Now we are in a position to integrate. Therefore, the y coordinate of center of mass becomes integral y dm divided by integral dm, right? The y we have to use here is the y coordinate of center of mass of that semicircle, which is 2r by pi. And dm now can be expressed as sigma pi r dr. And divide by integral dm is the total mass. I'm writing it as it is. This pi gets cancelled. 2 and sigma are constants. We'll put them aside. You get 2 sigma by m integral r square dr. Can one of you tell me what is integral r square dr? What is integral x square dx?
R cube by 3.
Integral x square dx is x cube by 3. So integral r square dr becomes r cube by 3. Therefore, the y coordinate of center of mass is 2 sigma by m into r cube by 3. We still have to substitute limits. In this entire integral, what was small r? Look at the diagram and tell me, one of you, what exactly is small r?
The small radius of the small
Rishi, your voice got cut. Radius of the small?
semicircular disk.
You don't call it semicircular disk. Semicircular disk will be this whole thing. It's a semicircular ring. Okay. The ring's radius is small r. Fine. Now from one ring to the next and so on, is small r a constant or a variable? It's a variable. Now we want to find out the position of center of mass of this entire semicircular disk. The disk is a collection of many rings like this, many semicircular rings like this. Tell me, what are the limits of R? Means, what is the radius of the first semicircular ring and the last semicircular ring that we have to consider? The semicircular disk whose center of mass you have to find out is a collection of many rings like this. What is the radius of the first semicircular ring and the last semicircular ring? First semicircular ring will be over here like this. In fact, it won't even be like that. I cannot show it. That's the first semicircular ring. And the last semicircular ring will be like this. What are their radii?
dr and r.
Pawan, can you repeat?
dr and r.
What is the meaning of dr, Pawan?
A small radius.
Small change in radius. It's not a small radius. It's indicated there in the diagram. No, dr is the thickness of the semicircular ring that we took. Its radius is r. Now, as the ring becomes smaller and smaller, what will the radius of the first ring be? Or what will the radius of the smallest ring be? Actually, I understand what you are thinking. You want to express a small radius, so you called it dr. But the first ring, okay, first semicircular ring, its radius will be tending to 0. Okay. You want to express a small radius, but you know dr is something which is very close to 0. Okay. So when you take limits for integration, the first semicircular ring's radius will be taken 0. Okay. And Pawan, you only tell me, what is the radius of the last semicircular ring that you will consider?
Capital R.
Capital R. Okay. So the limits for the varying radius of the rings will be from 0 to capital R. And when you substitute it, it becomes 2 sigma by m capital R cube by 3. Now what is sigma? Areal mass density. Areal mass density is nothing but total mass divided by total area. Area of the semicircular disk is pi r square by 2. M gets cancelled, r square gets cancelled. You will be left with 2 goes to the numerator, becomes 4. R square and r cube, 1r will remain, divided by, there's a 3 in the denominator and there's a pi in the denominator. You get the position of center of mass of this semicircular disk as 4r by 3 pi. Okay, pi is 3.14 approximately. So 3 pi is 9.4 something. So 4r by 9 point something, 4 by 9 of the radius. So it's less than half of the radius. Less than half of the radius means maybe the center of mass will be somewhere here. Okay, it is at a height of 4r by 3 pi from the base. That is what we have derived. Okay, just a moment. So basically what we are doing is we are visualizing the semicircular disk, which is an areal distribution, as a collection of rings. You all must have seen rainbows. No, rainbow has 7 colors. Okay. Do all the 7 colors have the same radius?
No, sir.
No. Which color has the smallest radius? Like which is the lowest color in the rainbow and which is the last color that you see in the rainbow? Anyone?
Red
Okay.
and violet, sir.
Okay, so the first one is red, and as we go higher, it becomes violet. You are saying, fine, let it be. Each color has its own radius, right? So the rainbow is not a full semicircle. It's a semicircular arc only. It has some width. In that width also, there are several elements. Each color is one element. Okay, you can even visualize this system like this. Not so wide also, but it's on the whole, it's a semicircular disk, and the semicircular disk is being considered as a collection of rings like this. What we struggled all this while, or what we struggled for all this while, is to express the area of one of these rings. Now see here in this diagram, in this picture, the width of the ring is very, is significantly large. But if you take it very small, no, how you express that area is the length, which is pi r. Okay, assume this radius is r. So this length becomes pi r with the, multiply that with the width. The width is nothing but dr from here to here. So that curved length multiplied with the width becomes the area of that ring element. And from one ring element to the other ring element, the radius changes, no? This is another radius. Here you have another radius. Okay. So for the first ring element, the radius will be 0. For the last element, the radius will be the radius of the whole system, capital R. So limits for small r will be from 0 to capital R. Okay. In this picture, that first radius, second radius are not clearly visible, but it will be from 0 to capital R. So let me just tell you the idea once again. The semicircular disk is considered as a collection of semicircular rings. Why did we take it as a collection of rings? Because we know where the center of mass of a semicircular ring lies. Like this yellow semicircular ring that I have highlighted in this picture. Okay. Its center of mass, it's not even proper yellow. Let's take it as green itself. Its center of mass is somewhere here. Okay. So all that mass that is shaded in this picture, we are putting all that mass at this point. Where is that point? At a height of 2r by pi. Why are we putting it at a height of 2r by pi? Because that is where the center of mass of a semicircle lies. So if you want to put all that mass at one place, you have to put it at this place. So all this mass dm was assumed to be present at a height of 2r by pi. Then we ended up with this integral y dm. Y coordinate for that mass is 2r by pi multiplied with dm divided by integral dm. We have to do something like this. So then we had to express dm in terms of dr. dr is nothing but the thickness. But you can't directly express mass in terms of thickness. Why? Because this is an areal mass distribution. Mass is spread over an area. So what you have to do is total mass by total area is equal to small mass by small area. And how are we writing the small area? Length into thickness. That way we get dm in terms of dr. Okay, you can call this sigma also. And then we are able to integrate it with proper limits. And we found that the center of mass lies at a height of 4r by 3 pi from the base. Is the derivation clear to all of you? Pawan, did you understand?
Yes, sir.
Saket, is it clear?
Yes, sir.
Okay, Yusuf. See, it's quite common to come across systems like this. And generally, no, in physics or generally in science, whenever you learn a property of nature, okay, whenever you study nature, what you first learn about is how particle to particle interaction takes place. How one particle of some object influences another particle. That particle to particle interaction, when you learn about it, you extend that to a system like a rod or a ring or a disc. So in that process of extending the ideas to bigger systems, you will have to treat bigger systems as collection of smaller systems. Like, when we tried to derive the position of center of mass of a rod, we treated the rod as a collection of particles. We took one particle of length dm, we assigned some length dx to it. Sorry. We took one particle of mass dm, we assigned a length dx to it and proceeded. Because why? The first thing we learnt about center of mass is how to find out the position of center of mass of a collection of particles. Okay, that particle idea we extended to a rod. We applied to a rod. Okay, we treated the rod as a collection of particles like this. Once we knew the center of mass, position of center of mass of a rod, we were able to tell the position of center of mass of an L-shaped object by using some extra ideas. Okay. Next, in the last class, we derived the position of center of mass of a semicircular ring. But here also, what did we do? We treated the ring as a collection of particles. One particle, one small particle of mass dm, length dl we took, and we did the integration. Okay, so generally this is how you are going to do things in science. You learn properties of particles, you learn a phenomenon about particles, you apply that to bigger systems. And see, it's very common. Most of you are trying to become or aiming to become engineers. In engineering, this has to be done anyway. In medicine also, it has some applications. That is why they expect you to know these methods. But those of you who are targeting NEET, you don't have to spend much time on this derivation, but remember the basics, because we'll be using this again and again for, as I said, moment of inertia, which will be derived in this chapter itself. Next chapter, gravitation, will derive something called gravitational field using these ideas. 12th class electrostatics will derive something called electric field using these ideas. Okay, so these ideas will be repeated over and over. So spend some time with this and get a hang of it. So what we discussed today is the derivation of center of mass of a semicircular disk. Right? And how did we do it? We treated the disk as a collection of smaller systems whose center of mass we already knew. What are the smaller systems whose center of mass we already know? We know that of a rod. And we know that of a semicircular ring. It was easier if we took it as a collection of semicircular rings. We proceeded that way. Okay, but in that process also, it's not as easy as it sounds. You have to find out the mass of that element, area of that element, all those things. Okay, fine. We'll continue in tomorrow's class. Tomorrow we will discuss how to derive the position of center of mass in a volumetric mass distribution. Linear distribution is done. This is an example of areal distribution done. We'll discuss what to do in case of volumetric mass distribution, particularly a sphere. Okay, full sphere, hemisphere, both cases we'll discuss. And today we actually looked at two methods. We first proceeded this way, but we ran into a very complicated integration and we gave up there. Okay, but this method is also useful, especially those of you preparing for JEE. Why this method is useful is because in here we took a uniform disk, that is fine. You may be given non-uniform disks. At each height, the density could be different. Okay. Now, if density varies from height to height, then you will have to treat it as a collection of elements like this only. You can't treat it as a collection of semicircles. You will have to treat it as a collection of rectangles. Okay. So in your next worksheet, you'll have problems like this. Step by step hints will be given. Solve it. You'll understand. You'll appreciate this procedure. You'll even understand the merits and demerits of this procedure. This that you see on your screen, treating it as semicircular rings, will be applicable or will be useful when it's a uniform mass distribution. That is what we have done now. You may even be given a distribution like this, density varying from radius to radius. Then you will have to treat it this way only. You can't solve it the other way. You can't treat it as rectangles and solve. You will have to treat it as semicircles and solve. Okay, so based on this, you will have problems in your next worksheet. And I'm telling you, the worksheets of this chapter are very, very important. If possible, if not possible every day, solve them at least on the weekends. Okay, fine. We'll continue tomorrow. Tomorrow regular class will be there, mostly from 7 to 8:30 or 7:30 to 9. I'll inform. Okay. Thank you all. We'll continue tomorrow.